Assalamualaikum warahmatullahi wabarakatuh. As we know, modern universities are currently manage massive and highly complex data. This includes student transcript, personal profile, CGPA, and financial records. As student enrollment climb into the tens of thousands, standard administrative work easily become overwhelmed and data intensive. The main issue here that unoptimized traditional sorting and searching method cause high system latency. This lead to frustrating system bottleneck, especially during peak period like semester registration and grading cycles. Therefore, our project focus on shifting basic data storage towards advanced algorithm optimization to keep the system efficient and responsive. Moving on to our objective, we have established three main goals for this project. First, to eliminate computational latency during database search by replacing slow sequential processing with high performance and algorithm. Second, to establish a structured data environment using efficient sorting mechanism to systematically organize large-scale student repositories. And third, to maximize search acceleration for a unique student and identify by significantly minimize the search space and processing time.
Next slide is algorithm selection. We use three algorithms to search to the record: linear search, binary search, and hash-based search. Linear search is used for faculty and semester. It is simple and does not shorter data, but is slower for large dataset. Binary search is used for CGPA and shorter record. It is faster because it works and shorter data and reduce the search step each time. Hash-based search is used for student ID. It is faster because it gives direct access to data. In summary, each algorithm is used for different types of data to improve system performance.
Hi, I am going to present algorithm analysis focusing on how we explain and apply our three search algorithms in the student record search optimization system. We selected and implemented each algorithm strategically depending on how the target academic attributes are structured. First, we have linear search, which we use as a flexible fallback mechanism. In the system, this is applied when staff search for unordered text files, such as filtering students by faculty or semester. Since the database is not indexed or pre-sort by this text file, the system can sequentially from index 0 to n-1 matching attribute. It is easy to implement, requires no sorting, and has a worst-case time complexity of BO of n. Next is binary search, which we apply to other numeric files, specifically locating or filtering students by their CGPA. Unlike linear search, this requires a prerequisite. The list must be pre-sorted. By applying a divide and conquer approach, we dynamically split the search boundary using the middle index calculation shown. This allows the system to isolate a student-specific academic performance bracket in seconds, yielding a rapid time complexity of BO of log n. Our primary high-speed retrieval system for unique key like the student ID or metric number is hash-based search. On system load, student ID are converted to unique bucket index. To handle collision gracefully, we implemented spread chaining with dynamic vectors. By maintaining a load factor threshold of 0.7, the system resizes and rehashes dynamically to guarantee an optimal, near-instant, average lookup complexity of BO of 1.
Linear search checks every single record sequentially. It's highly flexible because it works perfectly fine on assorted student records, but its efficiency depends heavily on where the data sits. In the best case, our target is the very first record, requiring just one comparison big O of 1. However, if the records are uniformly distributed, the expected case requires dividing the search space in half, giving us a formula of Tn equals to n plus 1 divided by 2. For 10,000 records, that means we expect about 5,001 comparison. In the worst case, where the record is at the very end or missing entirely, we have to examine all end records. For our database, that's a full 10,000 comparisons, meaning performance drops significantly as our data grows. Next, we have binary search. The strict requirement here is that our student records must be sorted by student ID. If they are, this algorithm becomes incredibly powerful by repeatedly dividing the search space in half. While the best case remains a single comparison, BO of 1, if we hit the midpoint immediately, the expected and worst case drop dramatically to logarithmic time big O of log n. Using the calculation, the n equals to log n for a database of 10,000 records, binary search finished the job in a maximum of just 14 comparisons. This makes it exceptionally efficient and highly scalable for a massive university system. Finally, let's look at hash table search, which uses the student ID as a unique key to map directly to a storage location. Under normal, uniform distribution, both the best and expected case run in true constant time, or big O of 1. No matter if we have 1,000 or 10,000 records, the expected number of lookups is just 1. Now there is a catch. The worst case can degrade to BO of n or 10,000 comparisons if heavy data collision occur and multiple records map to the exact same index. However, with proper collision management, hash table search delivers near instant retrieval. Because it's expected, performance remains completely flat as the database grows. It stands out as the most suitable and efficient choice for managing large-scale student record system.
Okay, now let's see at space complexity, which is crucial for preventing server congestion as our university database scales. As you can see on the slide, both linear search and iterative binary search are incredibly like on resources. They operate in place, meaning their space complexity is a constant of big O of 1 across all scenarios. They only need a few primitive variables regardless of whether we have 10 records or 10,000. On the other hand, hash table search trades space for speed. It requires linear space or big O of n across the board. To deliver instant lookups, it must allocate extensive memory for bucket arrays, dynamic collision chains, and resizing overhead. In short, linear and binary search keep memory low, while hash tables sacrifice more to maximize speed. Next, let's talk about the trade-offs. Choosing the right database engine is a balancing act between speed, memory, and flexibility. First, hash tables give us instant big O of 1 lookups, but they sacrifice server RAM. Binary search saves RAM, but compromises on speed and requires the data to be constantly sorted, which causes delays during heavy updates. Finally, consider flexibility. Hash tables are structurally rigid. If you try to search by anything other than the primary key, like faculty or CGPA, the system defaults to a slow linear scan. Binary and linear search handle these multi-criteria queries much more naturally. We must weight these factors based on our administrative needs.
Net comparative summary and discussion. 1. Syntax of feeding. No single algorithm is suitable for all search, so a hybrid approach is used. Linear search is used for faculty and semester with O n. Binary search is used for CGPA with O log n. Hash-based search is used for student ID with O1. 2. Comparison of algorithm. Linear search is simple but slow. Binary search is faster but need to short data. And hash-based search is the faster but use more memory. 3. Discussion and implication. Hash-based search improves speed during speed time. Linear and binary search are used based on data type. Overall, the hybrid approach improves system performance.
To conclude our presentation, this project proved that strategic algorithm design successfully mitigates computational bottlenecks in large-scale student database. Our proposed framework ensures high-speed filtering and minimal latency, even as the data volume grows exponentially. By evaluating our system using Big O notation, we have achieved concrete theoretical validation for both speed and memory efficiency.